Welcome. My name is Ray Xiong, and with my partner Yu Chen, this is our final project analyzing 56,000 fronts using deep neural networks. So in recent years, we have seen that artificial intelligence technology, especially deep learning, has achieved human-level performance in many complicated tasks such as image recognition, playing Go games, etc. The table here summarizes the competition between human and machine in 3 image recognition benchmark dataset. So at the meantime, we find out it is still very challenging to teach machine in things like art creation, composing music, or writing an article. So in the taxonomy of machine learning, we progress a lot in discriminate model, but there are still plenty of room to do in generative models. So if we take an even closer look, the key differences between the generative model and discriminative model is that the generative model tends to model the probability distribution of our data. So after that, we can generate the synthetic dataset. So in our final project, we challenge ourselves to teach machine write in its own style. So in order to do that, we split into 3 tasks. So by using the front dataset we found online, we try to create a lower dimensional embedding space, and we're going to map this embedding space to the fronts we have pixel by pixel. So after that, we will do some embedding analysis and visualizations, and finally, we will show you how machine can generate completely new fronts by itself. So first, let's take a look at our dataset. So we have 56,000 fronts, and for each front, we have 62 letters from capital A to capital Z, and from lowercase a to lowercase z, and from 0 to 9. So that's where the 62 comes from. So in all, we have about 3.5 million photos, and each photo is in 64 times 64. And here are some examples to show you that. And also, if you are interested in downloading our dataset, you can just type in your terminal wget with this address to download it. So the tools that we use for this project is mainly Python, Lasagna, Spark, and Google Embedding Projector. So the machine we have used is a Ubuntu system, and we hire it from AWS services from Amazon. And a little more about Embedding Projector. So it is a data visualization application which is open sourced by Google just a few days ago. And later we will show you we did a very cool visualization in this on about our embeddings. So next, let's look at our models. So the input of our model are very simple. We one-hot encode the font and the letter, and we use those 2 vectors as input. So in another word, we only tell the model, okay, this is font alpha, and this is letter A, and the network needs to figure out how it looks like. And remember that we have over 50,000 fonts, so it is a very sparse vector for this one. So we first project it into a 40-dimensional embedding space. And we have 4 hidden layers with leaky rectifier linear units as activation function. The output layer of our model is a 4096 vector, and you can think that as a 64 times 64 picture, and we calculate the mean absolute error, or L1 norm, as our loss function. And one more thing I want to mention here is we prepare the training and testing set by randomly splitting the 3.5 million photos. So you can imagine that we show the network how capital A looks like in font alpha without showing it B. The network then needs to figure out how capital B generally looks like by learning from maybe fonts beta or theta. And then it will infer how capital B looks like in form alpha. So here is some tricks we use when training the neural network, including adding a Gaussian filter, adding a dropout layer. So the initial loss is about 0.15 and the final loss is about 0.05. The training time is about 5 days. So here is the sample output. Here is just an example of the sample output. So as you can see here, our model did a decent job at most of the characters, but it gives up some of the difficult ones. For instance, a character with thin black line, for example the B here, is very hard to predict for the model. And also I want to show you that in our code. So first thing is here, the training one. So this is a function that we wrote for the mini batch iteration. And here we load the data, we load the model, we load the train function and testing function. So here, if you want to reproduce our result, you are welcome to run this on your GPU. And this is a loss it gets for each iteration. And for here is another predicting example. And we can say the same thing here for fonts. For characters with very thin lines, it is very hard to predict. But for those maybe thick one, for here, for this one, and this one, it shows with better quality. And to remind you that, so here, all characters are drawn from our test set. So the network hasn't seen any of them during the training. So all we are telling the network is A, what font it is, and B, what character it is. The model has seen other characters of the same font during the training, so it infers from those training examples to the unseen test examples as I show you here. So here is the true character looks like, and this is the predicted ones that our model has generated. Okay. So the next thing here is our embedding. So we find it is very interesting that our embedding actually looks like a multivariate normal. So here for the horizontal axis, we have 56,000 data points. And for the vertical axis, it's just the frequency of the values. So next thing is, so here is a t-SNE visualization of our embedding. So the t-distributed stochastic neighbor embedding, t-SNE in short, is a nonlinear dimensional reduction techniques. And we can see that in two-dimensional space, our data is separated mainly into two clusters, as shown you here. And in the middle, there is a cluster of very thin fronts. And you can see that if I enlarge it a bit. And also those thick fronts are clustered around those thin ones. So here is, I enlarge this area for you. And also, we will show you a t-SNE visualization in 3D. So this is the tensor board or the embedding projector that provided by TensorFlow. So here the first one is we do the PCA, we reduce the dimension of our 40-dimensional embedding space into 3-dimensional by PCA. And here you can see that these are the cluster of very thick fronts. And here are those ones with the thin ones. But we think that PCA did not do a very good job to completely separate those thin ones with the thick ones. So we run the t-SNE here. So it takes some time to load in the data. And the key here is we need to enlarge the perplexity. So for example 76, and then we click rerun. So very cool thing for the embedding projector is it will show you the whole process of t-SNE. So this is the initial states, and you can see the data, their positions are shifting. And we will wait the iteration here to maybe about 300. And you can see this whole process is a very cool visualization. We really want to show you here. And also you can drag and see how the process looks like if you like. And after 150 iterations, it turns that it will end up with a ball shape like, and we will wait for another 100 iterations here. So now you can see that our algorithm kind of converge since these letters are not flying everywhere. And so if we stop it, you can see that here is a very good clusters of the SIG fronts, and also here. If we turns out here are some very thin ones, and also here they are very thin ones. So it's kind of the half of the ball. Here, the half of the ball. Here is the the SIG fronts, and here are the thin characters. All right. So let's get back to our slides. So finally, we will show you how computer can generate its own front style. So the first way to do that is we can ask the network to produce a mixture of the fronts. So imagine that we can put Professor Lin's style here, and Eric's style here, and my style here, and my partner Yuchen style here. So by calculating the weighted average in the embedding space, our network can generate a new style as a mixture of our style. So for example, here, this one at the middle, it is just the weighted average from the four fronts randomly sampled from our dataset. And an interesting thing we find out when we play around it is that since some fronts use capital letter as the lowercase, by interpolating their embedding space, our network can learn the transition between the uppercase and the lowercase. So the red arrow actually demonstrates that. So it can shift between the capital letter to the lowercase letter seamlessly. So it is very interesting to observe that. So the second way to generate new fronts is by random perturbation. So we can ask the network to randomly choose. So we can ask the network to randomly choose one front, and we can add some uniform noise, very small noise, to the fronts, and that will give a completely new fronts. So here we made a GIF to show you that here are actually 20 new fronts that we generated by these methodologies. So the third way to generate is we can model our embedding space as a multivariate normal, and we can randomly sample a single point here as a completely new front, and you can see here. So this is a new front that we generated by this, and since you can observe here are the edges, for example here, of the fronts are not very sharp. So that's because our network, the loss function of our network is not it is not perfect. So if we have more time, we can definitely train it much harder and getting a better loss value, so that for generating new fronts, it will present you as a better quality. So in conclusion, in this project, we trained a generative network recognizing 56,000 fronts by learning a lower dimensional embedding space. We also visualize fronts embedding in both 2D and 3D. And also we wrote a script to read the HDF5 file into Spark RDD file system. And the potential marketplace for our network could be helping senior person write in their own style, or we can use that in calligraphy education. So for future work, we would like to explore generative adversarial network GAN for better loss value or the quality of the characters. And also we can change our current architecture by adding convolutional layer or maybe deconvolutional layer to further improve the loss of our network. So that's our final project. Thank you.